4.8 is Introduction to Acid-Base Reactions. So our outcome is I can identify species as Bronsted-Lowry acids, bases, and conjugate acid-base pairs based on proton transfer involving these species. So there are several definitions of acidity and basidity. The Arrhenius theory says that acids contain H plus ions while bases contain OH minus ions. So this is a simple definition, which makes it useful, but it also makes it not super accurate. So for example, what about ammonia? Ammonia is a base. So even though it doesn't contain hydroxide, it causes the pH of water to decrease. Or I'm sorry, causes the pH of water to increase and become more basic. So we use Bronsted-Lowry theory. So a acid is going to be a proton donor, while a base is a proton acceptor. We also form chloride as the conjugate base and ammonium as the conjugate acid. So for the following, give the conjugate acid or the conjugate base. So the conjugate acid is what we get by adding H+. Make sure that you take into account you are looking at a charged species, H+. So that means you need to pay attention to charges. Also notice that something like this carbonic acid can actually give up 2 hydrogens. So it could be in this form or in this form, meaning that this molecule is able to act as either an acid or a base, depending on whether it's protonated or deprotonated. For 2, we're just going to take away an H+. So again, we have to think about what charges are going to be present. So if I remove an H+ from NH4+, I'm going to be left with NH3. If I remove the H from water, I'm going to be left with a hydroxide. And if I remove the H from a hydrogen carbonate ion, I'm going to be left with carbonate ion. So to identify conjugate acid-base pairs, we have to look for a reactant and a product that are linked by the loss or gain of an H+ ion. So the thing that loses an H+ ion will be the acid, while the corresponding product is the conjugate base. The reactant which gained an H+ ion is the base, and its corresponding product is then the conjugate acid. So if we look at this first example here, this HSO4 and this SO4 are related by the loss of an H+. So this is an acid, this is my conjugate base, this is my base and my conjugate acid. Here we see that HCO3- becomes H2CO3. So that means that this right here is acting as a base because it's accepting an H+ from water, which is acting as my acid. So these are just several examples. We just want to connect them based on the loss or gain of H+ and then label them accordingly. Another important consideration is if the acid or base is strong or weak. So a strong acid or base is one that ionizes completely when added to water. So that means if I put 10 molecules of a strong acid, I'll get 10 H+ ions formed from it. So the strong acids are hydrochloric, hydrobromic, hydroiodoic, nitric acid, perchloric acid, chloric acid, and sulfuric acid. The strong bases are group 1 hydroxides, most commonly being potassium and sodium hydroxide. Also, the group 2 hydroxides, like calcium hydroxide, magnesium, and barium hydroxides. those are considered strong whenever they are at dilute concentrations, so less than a 10th molar solution, and we would consider those as strong. A weak acid or base does not ionize completely. So this is important because it's going to limit the amount of acid or base that is available to react. So you're going to experiment some with the PhET simulation. And for some results here, we're going to get some equations and some graphs. So I want to point out that whenever we look at the strong and weak acid, notice that one of them has an equilibrium arrow. And we see that for the weak acid, we have some of the undissociated HA that is present in the mixture. Whereas for my strong acid, all of that HA breaks apart. We also see something similar with our strong versus weak bases. But notice here they put an M. So all of our strong bases are metal hydroxides, so that's what that M is. And then for this one, a weak base is going to be a hydrogen ion acceptor, so we can form this BH plus compound as well as hydroxide. So we see that acids that are weak or bases that are weak do not fully dissociate and instead form a mixture of dissociated ions and undissociated acid molecules. So the bar graphs show that not all of the added acid or base actually becomes ions and breaks apart. So for strong and weak acids, the only difference in their equation is that the weak acid is represented with an equilibrium. All strong bases are group 1 or group 2 metal hydroxides. So that's why they are represented as MOH. And we have a regular arrow to indicate complete dissociation. For my weak bases, those are also described by an equilibrium. And those act as hydrogen ion acceptors, forming hydroxide ions and water. So if we add 10 molecules of a strong acid and 10 molecules of a weak acid to identical beakers, which one is going to be more acidic? So for the strong acid, the amount of H plus formed is going to equal the concentration of the acid. So all 10 molecules dissociate and we form 10 H plus ions. For the weak acid, the amount of H plus formed is much, much less than the concentration of the acid. So maybe of those 10 molecules, only one of them dissociates and we only get one H plus ion. So the pH simply depends on the concentration of those H plus ions. So in identical volumes, the strong acid is going to have a higher concentration of H plus, which means that it's going to have a more acidic, lower pH. Is it possible for a solution of a weak acid and a solution of a strong acid to have the same pH? Yes, because pH depends on concentration of H plus. So a dilute strong acid may have less H plus ions than a solution of a weak acid. So if they have the same amount of H plus in the same volume, they're going to have the same pH. Now, neutralization reactions can also be written as a net ionic equation, but it's always going to be in the formation of water. So the products are simply going to be soluble salt and water, and that means that they're going to be neutralization reactions. So we want to consider how each ion is going to react. So here we have KOH reacting with acetic acid. So we have a strong base and a weak acid. So the hydroxide ion is strong enough of a base that it's going to strip away the H plus from the acetic acid. So for stoichiometry purposes, we can assume that this is going to go to completion. There's no equilibrium here because there's a strong acid or base present that will react with the weak acid or base that's present. So we want to write some equations here. So we want to pay attention to the ratio of hydrogen to hydroxide. So since I've got two hydroxides here, I know I'm going to need two H pluses in order to neutralize it. So that'll form two waters as well as the aqueous salt magnesium perchlorate. The net ionic is just going to show the reaction between H plus and OH minus to form water. Here we have a 1-to-1 ratio of H plus and OH minus. So that's going to form one water molecule, and we're going to get some sodium cyanide as my aqueous salt. And again, my net ionic is just showing the reaction between the acid and the base, the H plus and the OH minus. So how do you identify a conjugate acid-base pair? So they are different by the loss or gain of a single H plus ion. So Bronsted-Lowry acids are proton donors and bases are proton acceptors. Why does water play an important role in acid-base reactions? So when we were identifying our conjugate acid-base pairs, we saw that water sometimes acts as an acid and sometimes acts as a base. So we call that amphotericity.